So now we get away from our very straightforward integrals as antiderivatives, and we start looking at some more advanced integral techniques. And so this technique of substitution is probably the most basic advanced technique besides just straightforward antiderivatives. So let's start with an example of the integral of the square root of 3x minus 4 dx. And so this is obviously an indefinite integral. And so what you might think is, okay, I need the antiderivative. And just for clarification, to be totally transparent here, what I'm going to show you is what a student might guess as to how to do this and why it's wrong. Okay, so the obvious thing to do would be to think of this as 3x minus 4 to the 1/2 power. And then you would do the antiderivative, and you got this power here. And so you would raise the power by 1. Sorry, that's your exponent. 3/2 is your exponent. And you've got 3x minus 4, and you would multiply the coefficient by the reciprocal 2/3. And you'd obviously put your plus c, okay? So it's a very good educated guess as to what you might do. However, if you check your answer via differentiation, if you differentiate this, the 3/2 and the 2/3 will cancel when you use your power rule. So that's good. So if we do the derivative, let's look at that. If we differentiate this, do we actually get the square root of 3x minus 4 back? Well, 3/2 times 2/3 is 1 times 3x minus 4. The power lowers by 1 to turn into 1/2. So that's good. The trouble with the anti-differentiation here is that we've got a chain rule going on, okay? Because when we differentiate, we still have to multiply by the derivative of the inside, which is 3, and this does not have a 3 in it, okay? So that's the issue here. You've got to be careful when you've got a function within a function and you want the antiderivative, because just like with differentiation in the chain rule, you have to inverse the chain rule when you do the antiderivative or the integral. So this does not work. So we introduce a technique called substitution to help us out, to make this integral look like something that we're comfortable with. So here's how it goes. We're going to break this into parts, and we know that we can integrate, we know how to integrate a square root. Okay, so we're not worried about leaving the square root inside the integral. The problem is we've got a function within that square root function. So what we're going to do is we're going to work on the inside function here, the 3x minus 4. We're going to work on this guy, and we're going to call that u. So we're going to let u equal 3x minus 4. Because I know how to take the antiderivative of the square root of just u now, right? The problem is if this is u and this is dx, they're not compatible because I need this to be a function of this variable. So if u is 3x minus 4, then I need to figure out the relationship between u and x as far as dx goes. So if u is 3x minus 4, then du dx, if I differentiate this statement, I get du dx equals 3. Okay? So now I have a relationship between dx and du. If I turn this expression into u, then I need this to be du in order to do the antiderivative. And now I have a relationship between u and x, a relationship between u and x and a relationship between du and dx. So what I've got so far, if I look at my integral, if I'm rebuilding my integral using our new variable u, then this turns into the square root of u, and then I need to know what dx is. So I've got to come over here, and I've got to think, basically it works like this. I'm solving for dx algebraically. So I can multiply both sides by dx, and I could divide both sides by 3, just using basic algebra, and I can see that dx equals 1/3 du. Okay, just some basic algebra. So what I can do now is I can replace my dx with 1/3 du. And now I've got a total shift in variable from all x's to all u's. And if we rearrange this, because this is multiplication by a third, that's just a coefficient. I can pull that outside of the integral, and I can write square root of u as u to the 1/2. I don't need parentheses there, sorry. du. And now I have a very basic integral, right? Just a very basic antiderivative. So now I can use the inverse of the power rule. Increase the exponent by 1 gives me 3/2. Multiply by the reciprocal, 2/3, times my existing coefficient, 1/3. And don't forget the constant c. And so now, when I'm looking at the original problem and I want to evaluate this integral, it's with respect to x. I want all of the antiderivatives of this function. So my final answer of this indefinite integral has to be back in terms of x. So what I'll do is I'll multiply my 1/3 by my 2/3 to get 2/9. But then I have to come here and look at my u, any place I have a u, and I have to replace it back with its x representation, because an integral of x needs to have an answer in x. So I get 2/9 times 3x minus 4 to the 3/2. Sorry, I should have used orange there. To the 3/2 plus c. And so that is the most general antiderivative of this function. You can see that the coefficient here takes into account the chain rule if you were to differentiate. If you differentiate this, you will get that function back. Okay, so that's a very good first example. What's really nice about this kind of substitution is the function that you substitute for u is a linear. And when you differentiate that, you just get a constant. Those are the easiest to work with. All you have to do to inverse the chain rule when you're dealing with a constant factor like this is multiply by the reciprocal of that constant factor, this 1/3. So that's the only adjustment we had to make to the original guess. Otherwise, it's the same thing as anti-differentiating something to the 1/2 power, but you have this extra coefficient in there to inverse your chain rule. Okay? All right, so you'll get better with that concept as you practice. Let's do many more examples now. Substitution can certainly be tricky at first. And the hardest part of it is knowing what to choose for your substitution. So let's look at the integral of 3x times x squared plus 5 to the negative 4th power dx. All right, so a little bit more advanced here, but if we look at x squared plus 5 and think ahead about its derivative, the 5 turns to 0. So what we're trying to do is pick our u so that the derivative of that also shows up somewhere in this function. And I know that the derivative of x squared is 2x. Now that coefficient of 2, we don't care about the coefficient. We can handle coefficients in any case. But the derivative of an x squared is going to be an x of some kind. And this particular function has an x, okay? So what we're going to do is we can kind of rearrange this integral into pieces. So I'm going to pull my coefficient of 3 out to the front because we can deal with coefficients. And I'm going to write my x squared plus 5 to the negative 4th here. And then I'm going to write times x dx. The reason I'm doing that is I'm breaking this into parts where the negative 4, the exponent of negative 4, we can integrate an exponent of negative 4. We don't need to worry about that. Okay? The problem is the function that's inside the negative 4 exponent function. So this guy is what we're going to call u, and this stuff over here is going to be a result of the derivative. okay? Because if this is u and I take the derivative, it's going to create an x and a dx, okay? So let's see that play out now. So now I will let u equal the x squared plus 5, and then du dx equals 2x. Now you're going to get used to this to where eventually you're going to go ahead and multiply both sides by dx. So you think derivative of this, you're going to think du. Sorry, I should have left that there. Eventually you're going to skip this step and you're going to jump right to du equals 2x dx. It's reminiscent of the chain rule, okay? But you can see that if you start here, which is good, maybe start here every time for a while until you get comfortable going straight to this step. All we do is multiply both sides by dx to get this. All right, so if I'm looking at the integral I want to rebuild, I can just carry down the 3, right? I can just carry down the 3. Then I have an integral of u to the negative 4th. And then I need to rebuild my x dx. So if I look at this and I want to get x dx by itself, I multiply both sides by a half. And so this means that I can replace x dx with 1/2 du. So one big tip when you're working with the derivative stuff, don't ever mix u's and x's, right? The coefficients can go on either side, right? The 2 could be over here or the 1/2 could be over there, doesn't matter. But you don't want to mix u's and x's. Everything with a u's on this side, everything with an x is on the other side. And by doing that, now you can replace all the x stuff with u stuff. All right, now the integral is easy. I can pull out this coefficient of a half to the front to get 3/2. And I can focus on, if I want to write an extra step here, now I just need the antiderivative of u to the negative 5th, which is u to the negative 3rd with a negative 1/3 coefficient, and then plus c. And then all that remains is to multiply the coefficients to get negative 1/2. I need to take and write my answer back in terms of x, so I need to replace u with x squared plus 5 again. And so this turns into negative 1/2 times x squared plus 5 to the negative 3rd plus c. And that's the most general antiderivative of this function. And if you go around playing with this, you'll see that if you differentiate this, you're going to get a positive 3/2 here as your new coefficient. This will turn into negative 4, which is good. But the problem is you'll have a 3/2 coefficient instead of 3. But then when you apply the chain rule, you'll multiply by 2x. And that 2 that results is going to multiply by 3/2 to give you the 3. And then the x is going to give you this x. So go ahead and try that derivative and see how it works out. Substitution is the inverse of the chain rule. Okay, that's what we're starting to see. It's becoming more clear as we go along. All right, let's look at another interesting example. X cubed over 2x to the 4th plus 3 dx. And the only way to get good at substitution is to sort of guess what you're going to substitute, try it, and find out why it doesn't work. You start to learn what works and what doesn't work. When I look at this, I'm thinking, well, I can see that I've got an x to the 4th, and the derivative of an x to the 4th is an x to the 3rd, right? So I'm going to let u be my denominator, and the plus 3 is good. I want to absorb constants into my u if I can, because the derivative of those constants are 0. So this plus 3 is not going to affect anything when I look at the derivative. So I'm going to let u equal 2x to the 4th plus 3. Then I'll differentiate both sides, and I'll see that du equals 8x plus 0, so I don't need to write that, 8x dx, okay? 8x cubed dx, sorry. And so if I'm looking at rebuilding this, I need to take my x cubed dx and rewrite it, and then I'm left with 1 over u, okay? So my x cubed dx, if I get it by itself, is going to be 1/8 du. So now I'm going to rebuild my x integral with a u integral. So this turns into the integral of 1 over u, and then x cubed dx is the same thing as 1/8 du. So thinking ahead, I'm going to go ahead and put my 1/8 coefficient out here and my du there. Okay? So we can start rebuilding the integral strategically by consciously putting coefficients out to the front and writing the integral in the way that we're used to. However, if you find that difficult, you can continue the same pattern of the earlier examples. So now we've got 1/8 times the antiderivative of 1 over u, which is the natural log of the absolute value of u, plus your constant. And then I just need to replace u with 2x to the 4th plus 3. And so that is the most general antiderivative of that function. And again, you can check it by differentiating to see that you actually get this function. All right, let's do another. Here's a good one. I'll try to build in some trig functions. What about secant of 4t times tangent of 4t dt? So in this case, we know how to anti-differentiate secant tangent. That's a common antiderivative. The problem is this 4t. So in this case, we'll let u equal 4t. Then this is going to turn into secant of u times tangent of u, and we know how to anti-differentiate that. The problem is it's not dt. I need to change this dt to du stuff. So I need to differentiate this relationship here to get du equals 4 dt. And here I need to replace dt now. So I solve for dt by multiplying both sides by 1/4, and I can see that dt equals 1/4 du. So if I'm rebuilding my derivative or my antiderivative, dt is 1/4 du. So I'll put my du here, and I'll put my coefficient out here. And now I've got an integral that I'm comfortable with, all in terms of u. So the antiderivative of secant u tangent u is secant of u, right? The derivative of secant is secant tangent. So the antiderivative of secant tangent is secant plus c. And then I just need to come back and write it all back in terms of my original variable t. So I replace u with 4t. So this turns into 1/4 times the secant of 4t plus this constant. Okay, so very interesting trigonometric example. The key here was recognizing that we know how to anti-differentiate secant tangent. It's that inner function that's causing us trouble. So just a general rule of thumb, you will commonly see that the inner function will be your u. Let's do another trig integral. So the integral of 2 plus cosine t times sine t dt. Maybe pause and try to work some of these on your own before I run through them. In this case, I'm going to let u be 2 plus cosine t, because if I differentiate, the 2 turns to 0 and cosine turns to a sine. So this sine could be absorbed in the derivative piece. So I'll let u equal 2 plus cos t. Differentiating, I get du equals 0 minus sine t, so I just get negative sine t dt, okay? So if I'm rebuilding my integral with all of that, then I have the integral of u, 2 plus cosine t is u. That's easy. And then what is left is sine t dt, this stuff here. So I need to get that by itself. So sine t dt equals negative du. So I'm going to put my negative coefficient out in the front. I keep writing my equals prematurely. Equals negative, and then I can put my du in there. Look how basic that integral is, right? This is u to the first power. I raise the power by 1, multiply the coefficient by the reciprocal, and that's it. And then I replace u with t stuff again. So I get negative 1/2 times 2 plus cosine of t, quantity squared, plus our constant. I don't know about you, but I find this pretty enjoyable. It's a great exercise because within one problem, obviously you're doing antiderivative. But here, when you go from u to du, you're also using derivative. So you've really got to be careful and cognizant of which way you're moving, derivative or antiderivative. So you really got to take your time as you run through that process. Okay, so last two examples, a little bit tougher. Let's look at, actually I'm going to do 3 examples because they're all good. You can't see too many, right? So let's look at the integral of secant squared x times e to the tangent of x dx. So you really have to think ahead and think about your derivatives. Whatever you choose to be u, you're going to differentiate to get du. So when I look at this, I see my tangent, and I know the derivative of tangent is secant squared. So I'm going to let u be my tangent of x function so that du is secant squared x dx. And you can see by doing that, I'm not worried about the e because I know how to anti-differentiate e to a power. So this turns into e to the tangent of x turns into e to the u, and secant squared, let's do this, secant squared x dx turns into du. So I've rebuilt my entire nasty integral all in terms of u very simply. Because luckily for us, the derivative of tangent yielded the secant squared directly. And so now I've reconstructed my entire x integral using only u's, and the antiderivative of e to the u is e to the u plus c, and then replacing u with tangent x, I get e to the tangent x plus c. Okay? So that's an interesting example. It's a matter of recognizing what function's derivative shows up somewhere else. Okay. Let's look at maybe one that could present some trouble. Yeah, we'll call this the last one. Let's look at the integral of x over x plus 1 dx. This one's tricky. There are lots of ways you could do this. You could probably do something with long division of polynomials, and I'm not going to get into that here. That's something we might look more at later if we get to partial fractions, okay? But for now, we can do this without long division. So what I'm going to do is I'm going to let u be the x plus 1, because that would be 1 over u, and I know the antiderivative of 1 over u. The trouble is the derivative of x is not going to give us this x, so we're going to have to see how that plays out. So let's, and this one's a bit unique, let's let u equal x plus 1, and then if I differentiate both sides, I get du equals dx plus 0, so just dx. Okay, so du and dx are equivalent here, which is interesting. So if we're reconstructing our integral, x plus 1 turns into u, dx turns into du, and on top I've got x. What do I do with this x? Well, it's really not that complicated. I can't write x because I can't mix x and u stuff together. But I have a relationship between u and x right here. I can solve this for x in terms of u. I could subtract 1 from both sides. So what I can do is I can replace this x with u minus 1. Now, you may be asking yourself, well, how is that integral any better than what we started with? Well, the nice thing is now we can take this fraction and we can split it apart. I can divide each term on top by u. So u divided by u is 1 minus 1 divided by u. And I've split the fraction apart into a difference, and now we can antidifferentiate each term independently. So the antiderivative of 1 is u, minus the antiderivative of 1 over u is the natural log of the absolute value of u plus a constant. So now I can take and I can replace my u's back with x plus 1's. So this turns into x plus 1 minus the natural log of the absolute value of x plus 1 plus our constant. So that one's a little bit less straightforward, but if you had to pick which of these to let equal u, you're going to pick the x plus 1 because the derivative of the 1 turns into 0. So you might as well absorb it into your u. Okay? So there are several examples of integrals using substitution. Practice a lot. It's going to be key to moving on to more advanced calculus or more advanced integration techniques in Calc 2.